remote sensing by Dr. Mehul Pandya, Space Applications Center, and another on atmospheric sounding by Dr. Manvinayak Shukla, Space Applications Center. And we have two moderators for these talks as well. The first moderator is Shri Ashwin Gujarati, who also works on thermal remote sensing and water quality. And the second moderator is Dr. Rishi Gangwar, who works on atmospheric sounding, retrieval basically. So I now hand over the session to the first moderator, Shri Ashwin Gujarati. Over to you, Ashwin.
Thank you, sir. The first presentation is by Dr. Mehul Pandya on overview of thermal remote sensing. So before the presentation, I would like to introduce Mehul, sir. So Dr. Mehul Pandya did his BSc and MSc in physics from Gujarat University and was university topper in both the degrees. He did his post-graduation diploma course in atmospheric sciences from the Joseph Fourier University, France, and did his PhD in physics. He has contributed in various R&D activities related to satellite remote sensing of biosphere, atmosphere, and astronomy. He was one of the team members of Mangalyaan 1 science team. His research interest includes optical polarimetric remote sensing for aerosols on Earth and Mars, greenhouse gas detection with hyperfine spectral observations and theoretical modeling, and terahertz astronomy for star formation. Dr. Mehul Pandya was a visiting scientist at NASA Goddard Space Flight Research Centers. He is a lead author in prestigious forums IPCC Intergovernmental Panel on Climate Change. He is also a recipient of many awards like ISRO Young Scientist Merit Award, ISRS PR Pishoroti National Award, and recently has received Gulbenkian Prize for Humanity as a member of IPCC. He has around 100 publications to his credits. With this introduction, now I request Mehul sir to share his knowledge on overview of thermal infrared remote sensing. Sir, to you, please.
Thank you, Ashwin, for kind introduction. I hope I am audible and my presentation is visible to all the participants. Good afternoon to all participants joining online this lecture. Today, I will be discussing overview of thermal infrared remote sensing. It is not a lecture. We would like to discuss some of the basics of thermal infrared remote sensing, physics behind it, and some of unique applications of thermal infrared remote sensing. So, generally, what thermal infrared remote sensing means, which we all understand very well. When some of the objects, living or natural, artificial targets like what I have shown here, if we try to understand its temperature, generally through thermometer, like what I have shown here is a photograph of certain house or a cat or a man or some picture of the natural landscape of soil and crop surfaces. What we generally see here in through thermal camera, some cold and hot temperature. So which generally we all understand what kind of information it would have contained. But what is the basis on which these thermal remote sensing works, that we should be actually discussing today. As far as thermal infrared range in the total electromagnetic spectrum is concerned, we all know that these EMR spectrum contains radio waves, microwaves, infrared, visible, UV, X-ray to gamma rays based upon frequencies, or you could say wavelength, which are proportional to energy. These EMR, they span a very big spectrum of frequencies or radiation, out of which the thermal infrared, generally people say it spans thermal infrared. Generally, it spans from 3 to 100, or loosely people say up to a few hundred micrometer. So this is a very, very important thermal infrared range. When people call visible, then near infrared, short wave infrared, a medium wavelength infrared, or thermal infrared, or long wave infrared, or far infrared, they talk about some of these frequencies. Generally, what is just these are one or two slides which I would like to just mention what kind of physics or random motion they are responsible for thermal infrared radiation. Any object which has got a temperature greater than 0 Kelvin, it would emit a radiation generally, which we understand that any object having minus 273.16 or greater than 0 Kelvin would radiate electromagnetic radiation, or whether it is solid, air, or whatever state the object is in. And what we generally think about various radiation and what human can see out of all the electromagnetic spectrum, the human can easily see the visible spectrum. That means 400 to 700 nanometer. The picture which I have shown here, it is a patch of small plantations where you could see what generally human can see during night time, and you see grass and some of the trees in it. But if you see through thermal infrared frequencies or thermal infrared wavelengths, suddenly you are able to see a person who is actually behind these bushes. So what visible could not see, or visible frequencies could not see, was observed through thermal infrared based upon the radiation with which this particular object or these bright objects, they are able to radiate some of the radiation in these particular frequencies. We'll discuss some of these things in slides to come in this particular discussion. Now, if we see some satellite-based information or satellite-based observation, here Landsat 7 ETM plus it is observing is place in Hawaii, a volcanic region, where you could see this is in shortwave infrared region band, that is somewhere around 2.1 micrometer, and you could see various landscapes, vegetation, rocks, and other things. But if you carefully see in thermal infrared band, a very bright object which is in the form of volcano is clearly visible, which was not observed in these data sets. What I would like to mention here, there are certain unique information hidden in thermal infrared spectral band, and it has got lot of applications. So we'll first discuss some of the basic principles, and then we'll discuss some of the applications as well. So either you talk about fluid or water vapor in the atmosphere. This is INSAT 3DS observation, and you could see 6.5 around micrometer fluid actually around Earth atmosphere. This is through infrared observation. Or if you simply see INSAT 3D image, which is in thermal infrared band, which is 10.8 micrometer spectral window, you would see something like this. This is simple top of atmosphere, what satellite would observe 1/3 of a globe in and around India and Asia region. And you could see Russia and some other part of Africa as well. So, but through certain methods, one can derive land surface temperature for these parts. And what you had seen, some of the radiant simple images were converted into land surface temperature data sets or land surface temperature information, which will give you a lot of information about surface processes as well. So what is very special about thermal infrared remote sensing as far as remote sensing of Earth or planetary science is concerned? If we see, Earth has its own temperature regime somewhere around 280 to 90, or let us say 300 Kelvin as far as various near surface objects are concerned. And you would see a very good infrared radiation actually emitted from Earth's surface in these regions. And one can understand the land surface temperature, sea surface temperature from these particular thermal infrared window. Thermal infrared observations are also quite useful in the quite colder planet called Mars. And we do, remote sensing for 180 Kelvin to 270 to 80 Kelvin, envelope over Mars as well. Or if somebody wants to understand the Venus, where you would expect some of the high temperatures, some of very, typical kind of temperature profiles, that also can be observed through thermal infrared remote sensing. Or if somebody wants to dig into deep sky, deep, for space science research activities, and if you were deep blue sky research as well, where you see various objects are uniquely observed at different wavelength region, either it is 2.12 micrometer, or if you see 70 micrometer, you don't see some of these objects, you don't see this trail of objects here. And ultimately what remote sensing scientists, they try to build a composite out of these data sets that is called multi-wavelength imagery. And this multi-wavelength imagery, as a function of various spectral bands, they provide you very detailed information, unique information as a function of wavelengths. And you could understand various properties of interstellar medium, dust particles, and different kind of, transitions of gaseous molecule as well. So these what I would like to tell you is thermal infrared remote sensing is quite useful in Earth remote sensing, planetary remote sensing, or for astronomy as well. Now, we'll try to see some of the basic laws which any remote sensing expert or professional has to understand. The first law, which generally people say, is a Rayleigh-Jean radiation law. What Rayleigh-Jean did, he actually modeled the outgoing spectral irradiance from objects having varying temperatures. So for example, if you have a 3000 Kelvin object with these kind of energy distribution equation, Rayleigh-Jean modeled that you would have these 3000 Kelvin envelope as a function of wavelength and the outgoing radiation. He also plotted then starting from very low temperature to 3000, 4000, 5000 Kelvin. It was okay. But when temperature basically was increased in this particular calculation through some of this classical physics theory, that these particular, temperature class was not actually, could not solve these particular wavelength region envelope. That means the high temperature energy distribution had a different kind of problem, and he could not solve this particular radiation regime. And what is generally, it should have been in somewhat visible and that kind of, observation near to visible ultraviolet wavelength region. And this particular anomaly is called UV catastrophe or Rayleigh-Jeans catastrophe. So what does it mean? For higher temperatures, these classical theory did not work well. So here comes the contribution of great Planck, where Planck basically based upon thousands of experiments, he made a beautiful distribution law 2 pi hc square upon lambda raised to 5, 1 upon hc upon lambda kt minus 1. That is a very detailed and beautiful law he actually proposed, where he could explain for temperature range of any kind of value, either it is 300 Kelvin or 6000 Kelvin, it could easily model the spectral radiance coming out of those objects. So Planck had a great contribution as far as black body radiation law is concerned. Then comes Wiens displacement law. Using Planck radiation law, which is basically giving you a distribution as a function of various temperatures. What we see here, the distinct feature of this particular Planck distribution law, the uniqueness of that law shows that if your object or black body is at 300 Kelvin, you would have its max radiation corresponds to a particular wavelength region, somewhere around 9.7, 9.6, 9.7 micrometer. If your object has a higher temperature of 500 Kelvin, it will have somewhere temperature range around less than 6-7 micrometer. As your temperature increases, the maximum radiation and corresponding wavelengths, it shifts towards lower wavelength region. And if you model or if you actually connect these L max corresponding lambda max values, that actually displaces towards lower wavelength regions. And that is what Wiens displacement says. Lambda max is nothing but 2897 divided by the temperature in Kelvin. So if you put any temperature at T and you put 2897, what lambda max you expect, you would get through Wiens displacement law. So that was a very nice explanation or practical utilization of Planck's law. Stephen Boltzmann basically also put a broadband flux emitted by any black body, which actually integrates the Planck function. That means all wavelength bands, whatever they emit for a function of or as a function of temperature of any black body, you basically sum the area under the curve, you would get the total EM radiation emitted by black body as a function of the absolute temperature. So which is nothing but, as I said, it is the area under the radiation curve or integral under the radiation curve. That is nothing but sigma T raised to 4 equivalent, where sigma is Stephen Boltzmann constant. This is also very important law as far as black body radiation laws are concerned. And based upon Planck's radiation law, any body, let us say for Earth atmosphere, one can understand what kind of radiation Earth would emit, what kind of radiation Sun would emit, what kind of various objects they would emit. This example of Sun radiating the total solar irradiance, and as we understand this surface, so-called virtual surface of Sun has a temperature of 6000 Kelvin. So based upon Wiens displacement law, the lambda max would be somewhere around 0.5 micrometer, and the top of atmosphere on the Earth surface or at the top of the Earth, you would have these kind of observation from the Sun. Okay, so there are examples or there are explanation about various radiation reaching to the Earth atmosphere, and through Earth atmosphere, basically radiation reaches to the surface. But there are lot of atmospheric constituents, namely some of the particulate matter, or majorly there are gases. They actually absorb the solar radiation, which are basically reaching to the Earth surface. I'm not going into detail, but what I would like to tell here is Earth has its own atmospheric layers, and the near layers, they have a lot of gases. These gases, they have their own spectroscopic manifestation. Radiation would be actually altered at these wavelength regions, and the radiations which are not quite hampered, they are called atmospheric windows, and remote sensings are being done in some of these open windows. So now we'll go to some of the thermal infrared details, that if we generally observe the Earth from the geostationary platform, this is a beautiful photograph of Earth in visible region. Same observation, if we see in thermal infrared, things would look quite different. This was visible, where you could see beautiful ocean, land surfaces, vegetation, soil, desert, clouds, beautiful streak of clouds, and whatnot, and watercolors also. But if we just see same region through thermal window, it would show you different kind of scene, where these are some of the temperatures which are being observed on the similar objects from thermal infrared. What is that? So now we are coming to how thermal infrared measurements are being made and what are the retrieval methods. So this cartoon shows that any surface which are emitting some radiation, that radiation, electromagnetic radiation, they are being actually observed by a satellite-based system, and that system, basically electromagnetic radiation is being captured, focused on the detector. Through detector, basically that detector detects that particular radiation, converts this electromagnetic radiation into electrical signal, and that electrical signal is being recorded in digital form over that particular satellite system. And those signal or those data sets, they are being transferred on the ground, and the image or data is being constructed of these objects, and people use these information about object through some of these images. This is total remote sensing process, where any object emitting the radiation, those objects are being observed through satellite system or instrument or sensor or payload, and that is being converted into image for further analysis. So now, what is basically use of thermal sensing? So we all know thermal sensing can be mostly used for deriving the land surface temperature or sea surface temperature, where these are some of simple examples I tried to put. That any body, that means if there is a object on the Earth at 300 Kelvin, that will have its own radiation multiplied by its own emissivity. That means there is a characteristics of any target which will show you the combination of emissivity and the brightness temperature, that means radiance from the surface, that is being observed by any target. And this brightness temperature is nothing but can be observed, computed through Planck's law, what we discussed few slides back. And any temperature can be, or any object with a certain temperature at certain wavelengths can be converted into brightness temperature, and that is basically manifested or observed through top of atmospheric radiance. And as we know, that the Planck's law, Planck has its own distribution function, and normally when Earth remote sensing is being done, Earth is somewhere around 280, 300 Kelvin temperature range, where if you see that temperature of 270, 280 to 310 Kelvin observed in 10 to 12.5 micrometer thermal infrared window will have beautiful atmospheric window with less perturbation compared to these, some of these bands of ozone absorption or water vapor absorption. These are quite comparatively lesser attenuated by atmospheric constituents. So remote sensing of Earth is being done by and large in 10 to 12.5 micrometers. So what we are going to discuss now is about some of these window in 10 to 12.5 micrometer, where water vapor is a player. Water vapor changes slight or alters the radiation, or carbon dioxide has some role to play. Otherwise, all other gases, they have almost negligible perturbation or impact on the 10 to 12.5 micrometer region. So as far as land surface temperature retrieval methods are concerned, there are various methods. There are various satellites which have a one window, that means single channel payload or sensor in 10 to 10.5 micrometer. So we develop single channel method for retrieving land surface temperature. If some sensors, they have somewhere around, two bands. So people use, or we use, split window method. If we have more than two bands, we generally use a temperature emissivity method. Or if satellite has multi-view angle capability, multi-view angle methods can also be observed. So we'll try to see very briefly what are these single channel, split channel, and temperature emissivity separation method of our this particular land surface retrieval subject is concerned. If we have single channel, then one can use this Planck radiation and related equations. You have top of atmospheric, basically radiation observed through a single channel method, and through radiative transfer simulations and some of the mathematical modeling, one can convert the brightness temperature or satellite level radiance measurement into land surface temperature. Here we did it for INSET VHRR, which had single channel method, and as I mentioned that VHRR thermal infrared image based upon single channel method can be converted into land surface temperature measurement, land surface temperature image, where you have radiative transfer modeling available offline with you. Lot of computations and forward modeling, they are being done as a function of varying temperature, emissivity, atmospheric profile, sensor response function, viewing geometry, etc. And they basically are, these computations are being used for computing the atmospheric functions. And these are offline computations already developed, and that goes into operational channel of single channel method implementation, where LST can be observed. And these were some of the initial observation over in and around India as a function of different time frames. We could compute the land surface temperature image of the India. The second method, where INSET 3D, 3DR, 3DS, there were three kind of, successive imager instrumentation available over INSET platform, where we have two bands, TIR1 and TIR2, which are basically placed in 10.3 to 12.5 micrometer range. What physics it actually implements is, if you see the transmittivity curve as a function of water vapor in the atmosphere, when atmospheric water vapor is quite low, you have very good transmittivity in both the bands. Now, as water vapor increases, you have hampered the signal as a function of this water vapor differentially in TIR1 and TIR2. And water vapor increases with a high number. These particular, both the bands, they have still steep change in their value. So this differential behavior of transmittance variation as a function of wavelengths, they are being captured through physical modeling, and they are being converted into lens surface temperature, where you could see we have used this split window method as a function of both the temperature region and a series of coefficients A1 to A6. They are called split window coefficients. They are being actually computed through or determined through lot of physics-based radiative transfer simulation activities. And this kind of split window coefficients, they are being used for retrieving lens surface temperature. So similarly, what we did for single channel method, what researchers they do, and we also compute a radiative transfer modeling computation, forward modeling we do for varying external atmospheric surface and sensor related parameters, and based on variety of these inputs, forward simulations, they are being used to determine set of split window coefficient A1 to A6, that too as a function of view zenith angle with various sub ranges of view zenith angle, because all these computation of atmospheric functions, they are function of view zenith angle also. And all these observations, they go into that particular, operational chain of 3D, 3DR, 3DS imager data sets. Split window algorithm is implemented and LST image is being generated. So I have shown here 2-time morning and afternoon images, lens surface temperature images from INSET 3D imager sensor. These kind of products are available at SAC ISRO's MOSDAQ portal, where every 15 days we have LST generated through various methods. So what generally this blue animation, somehow it is not working here, but what I wanted to showcase here is for these particular region of INSET observation window, one can observe every half an hour any pixel on these locations. And if you see the LST, they vary very nicely, and which is called the diurnal pattern of varying surface. Either it is cropland or desert or some of other targets. It will have its own temperature variation as a function of days also. So you can imagine the use of LST being observed through this geostationary platform can be useful for some of the process-based modeling, hydrological modeling, land surface process modeling as well. What we do, we generate or compute surface satellite-derived land surface temperature, and we then do in situ measurement of surface temperature over homogeneous patches or certain part of the land, where here we did it in Thar Desert, and for full day the satellite-derived observations were basically validated or compared with the in situ measurement. This is over desert. Similar exercise was also carried out over crop site of Gujarat, and which also showed very good results. So these are some of the validation of these thermal infrared modeling. And as I said, we have been doing LSTD modeling, that means land surface temperature diurnal modeling. I'm not going into detail of this, which will be very much useful. These data set, as I said, they are available at www.mosdec.gov, that is SAC, ISRO's data archival hub. You can have that. Now, after discussing single channel method, two channel, that means split window algorithm, I am moving to a multi-channel algorithm where if we have more than 2 thermal bands, one can use these multi-channel algorithm. And this is quite pertinent for some of the upcoming mission, that is Trishna mission, that is ISRO and French Space Agency CANAS mission, which is thermal infrared imaging satellite for very high resolution observation over natural resource assessment. The Trishna mission, which is having a very unique kind of configuration. Every 3 days it will observe the Earth with 56 meter spatial resolution, and which will have 2 payloads, one at thermal wavelengths and other observing the Earth at Vis-Near and SWIR payload. Vis-Near SWIR payload will be developed by ISRO's our Center, Space Application Center, SAC. Will be developing these Vis-Near payload, and CANAS is going to, or they are developing this thermal payload. And if you could see, it has 4 thermal channels, 8.6, 9.1, 10.4, and 11.6 micrometer as a central wavelength region. And these observations will be very much useful for, as we said, land surface temperature retrieval as well. And these 4 bands, they are placed at a very specific location where you could observe the Earth with little or less perturbation. And this can be useful for retrieving simultaneously land surface temperature and land surface emissivity as well. And what we at SAC, we have been developing, Ashwin and our team, they have been developing the temperature emissivity separation method, where it actually consists of RT modeling and various module of computation. And these, modules are quite interesting to understand, where RT modeling and some of the mathematical modeling, they go into those implementation, and the simultaneous retrieval at surface temperature and emissivity is being developed, where you have various modules called NEM module, ratio module, MMD module. They have been actually developed specifically for mission like Trishna or some of the proxy data of Aster or EcoStress as well. So we have developed, or we have been developing these kind of observations or modeling. And what, depending upon our method, some data sets of Aster, they have been converted into temperature, and the standard product are being validated, and they are in quite good agreement. Or emissivity for these same data sets from tests, they have been also tested and validated or compared with our data sets. The last section which I'm going to discuss is about active fire detection using infrared observations. We know forest fire or agriculture burning, they take place, which has a temperature greater than 350 Kelvin, 400 Kelvin, 450 Kelvin. So what generally physics says, that higher temperatures can be observed at 3.9 micrometer range, which will give you very good understanding about the forest fire or active fire detection. And people have developed, we have also developed some of these algorithms. This is also called from infrared observation forest fire detection algorithm. This particular slide shows a part of Punjab Haryana region from INSET 3DS observation in November 2024 timeframe, where agriculture burning activities takes place as a function of time in the day, whereas day progresses, the agricultural residue are being what you can say, they are being burnt and they are being actually observed through geostationary platform. So some of these active fire detection algorithms are also being developed, and they are also useful as far as thermal sensing is concerned. So some of forest fire, active forest fire locations over Uttarakhand, they were also observed through, these are wildfire or forest fire activities. They are also being derived through infrared observation. So using temperature observation, using thermal infrared observation, there have been lot of data sets can be, or products can be derived of surface temperature, land surface, sea surface temperature. They can be used for evapotranspiration and surface fluxes computation. One can observe surface emissivity, urban heat island effects, hydrological modeling, thermal inertia, air temperature, water temperature, crop stress and moisture stress related studies, use of some of these parameters in land surface model, or use of thermal sensing in atmospheric sounding research also, which I think subsequent lecture by Dr. Manvinayak Shukla will cover some of these aspects. And thermal infrared, they are also can be used in planetary science or space science research activities also. So these are some of the examples I showed you about thermal surface temperature, land surface. These are for sea surface temperature, and there are a lot of applications. So I'm not going into these details, but applications are available as far as it can be useful for agricultural, hydrological, atmospheric modeling, and people have been using it for various applications. And this was our study, which showed how urban area of Ahmedabad actually increased in decadal time frame, and Ahmedabad region was converted, has been converted into urban heat island. So some of these applications also show is very great, power of satellite remote sensing. And last but not the least, these infrared observations, they are being used for deriving trace gas and greenhouse gas constituents of the atmosphere, which are very much useful for air quality, climate change, and some of the applications related to atmospheric sciences also. So greenhouse gas can be also useful, as if you see some of the thermal bands of these gases, they can be useful for observing these toxic gases as well. So here I would like to stop for today, and thank you very much for your patient hearing, and thank you, and over to you, the moderator, for any further question answer session. Thank you.
Thank you, sir. We truly appreciate the knowledge you shared with us. On behalf of everyone, we would like to express our sincere thanks for your informative and thought-provoking presentation. Before ending our presentation, I have gathered some of the questions from the chat box. There were many questions, but I have tried to club based upon their themes. So the first will be regarding sensor system studies. Like the first question is, how do ISRO sensors decide which IR band, NIR, SWIR, MWIR or LWIR is used for a specific missions, and how the geostationary or polar orbiting satellites have been used.
Okay. So what you are saying or asking is how any sensor or thermal infrared system is being designed or decided. So as we discussed and showcased, the decision or the finalization of the thermal band is based upon your object which is to be observed. For example, if we are observing earth surface which has a temperature generally varying between 270 to 80 Kelvin to 320 Kelvin, that means if we understand it is average temperature of 300 Kelvin. So if you put 300 Kelvin in Wiens displacement law, which is nothing but lambda max is equal to 2897. That means it is somewhere around 3000 if we approximately understand. So lambda max 3000 divided by the temperature regime which you would like to see. Let us say for Earth, it is 300 Kelvin. So 3000 by 300 Kelvin. So what you get answer is 10 micrometer. So your optimum window is 10 micrometer. Now, if you want to observe a temperature regime of, let us say, Mars surface, which has a 200 Kelvin temperature. So you put temperature range as 200 in Wiens displacement law. So what you get 3000 by somewhere around 200 to 20 Kelvin, you would get answer somewhere around, what kind of 3000 by 200 is, yeah, somewhere around 14, 15 micrometer. So what you generally have, you have to shift to 15 micrometer range. If you want to observe, as I mentioned, high temperature regime of forest fire or agriculture fire, where temperature regions are 500, 600 Kelvin, you have to shift towards 5 micrometer. So window is decided upon object. The second most factor in deciding these spectral band is the atmospheric opacity. Whether the atmospheric constituents present in your medium, that means in Earth, whether they are opaque or clear, that means you have atmospheric window available in, let us say, 10 micrometer spectral range. So answer is yes, 10 micrometer range is quite transparent to radiation. So people decide to do 8, 9, 10, 12 micrometer probing of Earth surface. If you go to some other object of high temperature range, as I said, for fire, 3.9 micrometer window is found suitable because that particular window is quite sensitive to high temperature and it is also having less perturbation from atmosphere. So these are 2 to 3 physics based criteria which are being understood or which are being considered, and depending upon the availability of various components, expertise, then engineers, they design those systems for specific application. I think I answered the question.
Yes, sir. You have very well answered about the band selections for the specific missions. The other question which I have clubbed from multiple observations was about the accuracies and the observations, like how the TR sensors could be used in weather conditions like rains, snowfall, and smokes from the burning fires.
It is a very important question and it is a detailed question as well. The accuracy of observation is one thing. The instrument will have its minimum accuracy, which is being generally typically represented as a figure of merit, NEDT, noise equivalent temperature, detectability. So generally good instruments would have NEDT ranging from 0.1 Kelvin to 0.3 Kelvin. So now instrument has got, let us say, 0.1 or 0.2 Kelvin accuracy. From that instrument, you observe some of objects and then you retrieve through certain algorithm. So you would make certain mathematical modeling to invert the brightness temperature to your surface temperature. So your model may add some more inaccuracy. So some of these factors, they add up and they actually arrive at a last number, which is called model accuracy or retrieval accuracy, which are generally, they range in 0.5 Kelvin to 1.5 Kelvin as far as land surface temperature is concerned. Sea surface temperatures have a very stringent requirement of very high NEDT and in turn very high retrieval accuracy as well. So that is aspect number one. Aspect number two is if you have a perturbing atmospheric constituents of smoke, haze, and some of other constituents, they are going to deteriorate your observation. And there are certain methods where researchers try to decouple or normalize the effect of some of these. But if you haze, smoke, and very great blanket of smoke is there, they hamper the observation. It makes surface temperature retrieval almost next to impossible. So the thermal infrared window, if it is transparent to some of the gases, molecules, atmospheric water vapor, it can get through, it can derive the surface temperature quite accurately. But if you have a big blanket of smoke, it is going to hamper your thermal infrared observation, where you won't be able to give accurate estimation about the surface temperature.
Thank you, sir. So based upon the transparency in the atmospheric window, the detection is possible in thermal observations. We had many more questions, but I would like the students to ask the questions with the auditor with the mail given provided with you. With this, we end our lecture. And again, I would like to thank Dr. Mehul Pandya for his expert lectures and very informative and thoughtful presentations. Now, I would like to hand over the.
Thank you, Ashwin. And I thank organizers, Dr. Jagdisha, Dr. Praveen, Dr. Tipi Das, Dr. Janardhan, IIRS team, ISRO headquarter team for giving me this opportunity. Thank you. Thank you very much.
Thank you, Dr. Mehul Pandya, for your excellent lecture. So now we will move to the next lecture. The moderator is Rishi Gangwar. Over to you, Rishi Gangwar.
कुछ लेना ये नॉर्मल है तुम्हारा
Vinayak Shukla completed his graduation in 2000 from Ramjas College, Delhi University, and done his post-graduation from Indian Institute of Technology, Delhi in 2003. He joined Space Application Center, ISRO Ahmedabad, as a scientist in 2006. He completed his doctoral thesis on study of thermodynamic structures of tropical atmosphere using INSAT 3D. He contributed towards the development of operational retrieval algorithms and its validation for various meteorological parameters such as temperature and moisture profiles, cloud top properties, cloud marks, etc. from Indian meteorological satellites such as Kalpana 1, INSAT 3D, Megatropics, and INSAT 3DR. He also made significant contribution in monitoring and intercalibrating infrared visible and shortwave infrared sensors on board Kalpana, INSAT 3D, 3DR, 3DS, Imager, and Sounder. He is visiting scientist to University of Wisconsin, USA in 2010. He received ISRO Team Excellence Award for IMDPS project in 2014 and Pisharotti Memorial Award by Indian Society of Remote Sensing ISRS in 2022 for his outstanding contribution in the field of satellite meteorology and remote sensing. Most of his contributions are published in high impact international and national journals. He has more than 50 publications in the journal, reports, conference, and symposium. Since April 2023, he is heading the Space Science Division SESG IPSA in Space Application Center. With this brief introduction, I would like to request Dr. Manvinayak Shukla for his presentation.
Thank you, Ashwin. Thank you for your introduction. So, first of all, I am thankful to ISRO headquarters and IIRS team for giving me an opportunity to present this topic on from the atmospheric sounding. And I am also thankful to Mehul sir because he has set some of the ground for me for this presentation. So now I'm going to start my presentation. So this is so our slides are visible to everybody.
Yeah, visible. Please go ahead.
Jagdisha sir, are slides visible to you?
Yeah, visible in full screen. You can go ahead.
Okay, so I believe that slides are visible. So this is basically a very brief introduction to the fundamentals of atmospheric sounding. And this topic is very interesting from the satellite meteorological point of view, because before this presentation, we have heard that we can understand some surface properties from the thermal remote sensing. But it is not just for the knowing the surface properties, but it is a kind of a estimation of the full profile. It means the knowing the information from the surface to the almost like 100 kilometer or 85 kilometers from the surface to the atmosphere. So basically, most of the tropospheric information, whatever is occurring in the weather phenomena. So basically, it is a kind of a remote sensing of the full profile. So here, primarily, we are concentrating on the temperature and moisture profiles and some of the glimpses of the gases that we can infer from the indirect measurement of the through the indirect measurement. So basically, why we do know we require these kind of temperature and soundings of the temperature, moisture, or other gases. So basically, the whole gambit of weather forecasting, climate monitoring, and understanding the various weather phenomena, or if we want to understand the various climatological phenomena. So not just for the forecasting, because the base of forecasting is basically rest on the total foundation stone of the understanding of the various physical phenomena that are occurring throughout the globe. And it is basically, it requires the three-dimensional information of temperature and moisture. So the prediction of the atmospheric state at the different scales, and the not just for the local weather in the shorter time scales, and the short rain forecasting, medium rain forecasting, or maybe the extended rain, seasonal or climatic scales. On all these kind of observations, we require the data. And this data can come in form of surface observations or the upper air observations. So these upper air observations are basically nothing but the atmospheric soundings. So these meteorological observations of pressure, temperature, humidity, like the full profile information from the surface to the all above atmospheric layer, we require these kind of information for all these applications, as I have mentioned. So what are the state of the art, that from where are we getting these kind of information? So these atmospheric profiles are available from various satellite observations, and I have listed some of the important observations in this table. So the temperature profile comes from the ETOPS, AMSU, IIRS, MODIS, GIFTS. Not from the GIFTS, basically it is a IIRS satellite from the FY4A, 4B Chinese satellite, and INSET 3D series of satellites. Similarly, the humidity profiles are also available from many of these sensors. So these are the some of the one-day coverage over India from the various sensors such as IIRS, CRIS, and IASI. So basically, it shows that these observations are coming from the low Earth orbiting satellites. These are the examples of these soundings at a particular level. At a particular channel which is speaking at a particular level. So it is showing this information, and it is very much clear that some of the observations are available at some of the local time. So it is not providing the coverage at all the times of the day. Now, based upon I assume that all these audiences has some information about the geostationary satellites and the lower Earth orbiting satellites. So I'm not going much into the detail of these orbits. I believe that the audiences are aware of these capabilities. So as I have told in the previous slide, that the observations from the low Earth orbiting, so it has some its advantages, and some of the advantages lies with the geostationary orbit. So for example, the low Earth orbit basically provides the global coverage, but the geostationary satellite provides only the regional coverage. It means they cannot provide the information throughout the globe. If we want information for the whole globe, we require the ring of satellites on the geostationary ring. But the major advantage of geostationary satellite is that they can provide the high temporal resolution. That means we can have the data over with the lesser, like the higher frequency with respect to the time. And here we do have low temporal resolution. They can provide the information though over the global coverage, but on the certain period of time only. So most of the hyperspectral IR soundings are available from the LEO Earth orbit, though in the recent development, the Chinese geostationary platform are also providing some hyperspectral IR sounding through the geostationary orbit. And even with the present technological advancement through the geostationary, we cannot have the microwave soundings or the GPS, the receivers, they are not available from the geostationary platform. So that's why there are some advantages of the low Earth orbit, that we can have microwave soundings from the low Earth orbit. So the atmospheric sounding, this is the one thing that they can have from the geo or LEO. The another thing is that we can have sounders which are the multispectral, means where the it's a spectral resolution, lambda by delta lambda is much less than the 100. So they have the less number of channels with the relatively larger bandwidth. And these multispectral sounder have some sort of horizontal resolution of the order of 10 kilometer for IR and 50 kilometer for microwave. And it's a lower vertical resolution, like 5 kilometer for the water vapor and 3 kilometer for the temperature. And its accuracy is also around the 30% for water vapor and 1 to 2 Kelvin for the temperature. But the hyperspectral sounders, sorry, such as IIRS, IASI, ATMS, JIRS, etc. So their horizontal resolution is around 10 to 20 kilometers. And but the major advantage of this sounding system, it has the better vertical resolution around of the order of 2 kilometer for water vapor and 1 kilometer for the temperature in the lower troposphere, and with the better accuracy of 10 to 20% of water vapor and around 1K for the temperature. And other than that, with the limb sounding, the best example with the GPS radio occultation, so like CHAM, SAXI, Cosmic, OceanSat 2, Megatropis, etc. So they have the very good vertical resolution and the relatively higher accuracy of the temperature and water vapor, but the poorer horizontal resolution. So if we see that like there are some again pros and cons of the different kind of systems. So, but the major gap areas we can find here that the higher resolution sounding under the cloudy conditions. For example, if we want better vertical resolution, then we have to go for the hyperspectral sounder in the IR, but they cannot provide under the cloudy condition criteria. And similarly, we cannot, like with the present technological constraint, we cannot put any microwave sounding instrument on the geostationary satellites. So this slide basically presents the evolution of atmospheric sounders from multispectral to hyperspectral. So here in the 80s, we do have HIRS kind of satellite, and they have the series of satellites over the NOAA platform. And then the GOES program also started. It is the geostationary sounder, multispectral sounder. Then there is an era for the hyperspectral sounder with the advent of IIRS, and then the launch of IIRS basically totally changed the arena of the hyperspectral sounding with the 8,461 channels. And after that, then on the repeat of CRIS, but with the major advancement, repeat of IIRS, there is a major advancement in terms of CRIS, which is the again LEO satellite, and the with the recent launch by the Chinese FY4A and 4B, there are geo hyperspectral sounders. So basically, with this thing, this is the very brief description, or you can say that the history, or maybe the orbits and the various spectral criteria for the sounders. So before going into the detail of Nadir viewing sounders, I will just briefly discuss about the limb sounding. So this is the radiative transfer equation as it has been previously discussed in the last presentation by Mehul sir. So basically, it is about the radiance observed at the top of the atmosphere. So basically, it has three terms: emission by the surface, then the emission by the atmospheric layers, and then the reflection by the atmospheric layer, absorption, and then re-emission by the atmospheric layer. So basically, these are the three terms. So here, as we see in the figure on the right side, the upper figure on the right side, basically limb viewing is something like we are not looking downwards, but we are looking kind of a sideways to the atmosphere. So here we see that as where my cursor is moving. So basically, if it is our instrument, it is looking for the atmosphere in the sideways direction. So here we see that since no source here on this direction, so basically what it is observing is just the emission from the atmospheric layers. So that's why I have put the cross figures on these two terms. It means it does not see the emission from the Earth surface. So that's why this term is not useful for the limb sounding. And similarly, the re-emission by the reflection by the other atmospheric terms are not very useful because of the emissivity on the wavelengths on which it operates. It is nearly equal to 1. So that's why we can assume this term equal to 0. So that's why only the center term, which is basically the absorption emission by the atmospheric layer, is very useful. So here it looks in this direction. For example, at one angle, it looks towards the one layer of the atmosphere. When it changes the looking angle through the atmospheric layer, it is looking for the point B through this layer of the atmosphere, and similarly from point C to point B to point A. So in that way, it looks towards the different layer of the atmospheric layers. So here what the advantage is that here we see on the bottom panel that the weighting functions are very sharp. It means, for example, if we see at the C, so only for particular height H3, it means this atmospheric layer will sense only with the S3. It means suddenly it will look towards this atmospheric layer S3. And though if we go towards the larger path length, but primarily the contribution is coming from this atmospheric layer, and some of the contributions are also coming from the above atmospheric layer, but that contribution decreases as we go away from this looking angle. So that's why the suddenly it peaks at a particular height. It means the maximum contribution is coming from that layer, and then it suddenly decreases. And so that's why if we see that these weighting functions, it means weighting functions, I'll discuss it detail when I come for the Nadir wing sounding. Basically it tells that these particular instrument, how much contribution is coming from a particular atmospheric layer. So here weighting functions are very sharp. So that's why it has a very good vertical resolution. And since there is no background like emission from the earth and other major backgrounds are there, so background is basically cold and uniform. So that's why it has a very high sensitivity and the long path length. So if we want to measure some trace gases, so because of the larger path length, it gives a lot of sensitivity about those gases. So here we can also have a sounding of the various gases because of the very high sensitivity and the low background and a very high vertical resolution. So this is the major advantage of limb sounding. Since because of the high path length, so there is a more absorber in this path length. But the major disadvantages is the poor horizontal resolution, because we see that we assume that this horizontal point is just below this this point where we are measuring the height. Since it is a large surface, so even the tangential point, when it touches to the surface, it represents a larger geographical region. So that's why its horizontal resolution is very poor. So that's why there are various applications where we require very high vertical sensitivity, but we can compromise on some sort of the horizontal resolution. Like suppose if we want to know the concentration of ozone or may some of the trace gases like CO2 and other gases. So this kind of limb sounding is very useful because of the high sensitivity towards the trace gases and other gases. And we can have some, we can compromise on the horizontal kind of resolution. So this is basically a limb sounding. And here this thing should be very much clear that we are looking through the atmosphere from the sideways, not from the towards the Nadir direction. Now I am coming to the Nadir wing atmospheric sounding, and I'll discuss about its theoretical basis. So here, as it has been discussed in the previous presentation, that basically the Earth atmosphere system follows the black body distribution. And here it is showing that the black body distribution at the different temperatures, and it is the radiance on the y-axis. On the x-axis there is a wavelength. And here we see that the various temperature from 200 to 300 Kelvin, and it shows that the black body distribution with this black curve as shown by my cursor is basically somewhere between 280 to 300 Kelvin. And here we see that a large dips are there. So basically these dips are basically the absorption by some of the gases. So here it is the major absorption by the ozone, CO2, water vapor, and here again around the 4 micron, again there is absorption by CO2. So this for sounding, we actually exploit the absorption criteria by some of the gases. So suppose if there are no absorption, so obviously this would have followed a particular black body curve. Okay, but due to absorption, it has dipped in some of the ranges. So if we see on the figure on the bottom, so basically there are, we can roughly see that at the top of the atmosphere, radiance is basically contribution is coming from all the way down from the surface to the total all of the layers above the surface. For example, let's say on the bottom figure, the first contribution is coming from surface to the all the way up to the top of the atmosphere. Then the contribution from the first layer above the surface, then the second, third, fourth, fifth, and sixth, and so on. So it means, if since we have already told that the layers above the surface not just absorbs the radiation, but it also basically emit the radiation at a particular temperature. So it means whatever the contribution we are receiving at TOA, like the top of the atmosphere, is basically is the summation of all the contribution which is coming from the surface and all the atmospheric layer above the surface. Now what happens? What happens, for example, if we, again, this is the radiative transfer equation which I have already explained in the previous slide. So here we see that, for example, like it is the zoomed version of some of this point where there is a strong absorption, just like one line. So this is the zoomed version of the one line. So here we see that one particular absorption line is basically consist of this is basically consist of the total spectra, and there are three wavelengths: lambda 1, lambda 2, and lambda 3. So this shows that there is the highest absorption at the lambda 3 wavelength. It means here at this particular wavelength, there is the maximum absorption, and at the lambda 1, there is the least absorption. It means if any wavelength which is passing through the lambda 3, basically it is having the highest absorption, it means the maximum absorption will take place. And somewhere there is another wavelength lambda 2 where there is a somewhere, not like you can say that the maximum absorption or minimum absorption, it is somewhere between. So now on the like figure B, it shows the transmittance curve. So transmittance curve shows that as we go, like transmittance, it means how much emission will transmit from particular layer. So it is evident from this figure that for the lower surfaces that almost no radiation will reach, because there is of the high absorption. It means even though the radiation is emitting from the all the atmospheric layers from the surface and below, but because of the highest absorption, that the no radiation from the lower level, because it will travel through the longest path length, so it will be very difficult for the radiation which are emitting from the lower surfaces will not reaching to the top of the atmosphere. But as we go above the pressure level, it means above in the atmosphere, then there will be the bit of the transmittance, because the path length above those atmospheric layer are a little bit less. So some of the radiation will reach to the top of the atmosphere. But for the lambda 3, what will happen? For the lambda 3, this is the least absorption. But here it is a point worth mentioning is that the transmittance we are talking about of this total spectra for lambda 1 and lambda 2, lambda 3, this is for the absorption gas. We are not talking about the absorption spectra in the window channel where there is no absorption of any of the gas. So this point is really very important, because for the sounding we must choose detectors or channels in such a way that which lies in some of the absorption spectra. So here, that's why it is like very interesting to see that the transmittance is not equal to like 0 or 1, because it is in the absorption spectra, though it is the least absorption. But even though some of the absorption, some of the radiation will be absorbed, but the transmittance from the surface will also, some of the quantity from the surface will also reach to the top of the atmosphere. So as we go above in the atmosphere for the higher pressure level, the transmittance will increase, and at the top of the atmosphere, it will reach up to the maximum value. So in between, the lambda2 behavior of the transmittance will vary between lambda1 and lambda3. It means it will absorb, it means some of the atmosphere from the lower level will also reach to the top of the atmosphere, but not as good as by the lambda3. This is the weighting function. Basically, it shows here, if we plot a kind of a density plot of the atmosphere, then the density of the atmosphere is highest at the surface, and it reaches to a very low value to the top of the atmosphere or at the higher pressure levels. So even though this like the higher transmittances of the lambda3, but the density will be very small. So by multiplying these two factors, we'll have some shape like this: lambda1, lambda2, and lambda3. So these shapes are basically the weighting functions. So the first weighting function corresponding to lambda1 shows that the maximum contribution will coming from the highest from the levels, but for the lambda3 you'll see that the maximum transmittance is coming from the very high pressure levels. It means the atmospheric level lambda3, which are the highest absorption, will sensitive to the pressure levels, will sensitive to the atmospheric layers which are peaking into the higher in the atmosphere. But those are very sensitive for the lambda1, which is very like least sensitive. They will sense to the near to the surface, because lambda1 you'll see that the since it is the least absorbed, so the maximum contribution will coming from the surface, and as you go on the above, it contribution will decrease. So that's why the maximum contribution will come from the surface. So lambda1 is showing the channel which is least sensitive for the atmosphere will sense to the surface. The lambda3, which is the highly absorptive, so that channel will peak into the atmosphere. So thus by appropriately selecting the wavelengths, it means wavelength where it is in the highest absorption band or it is in the least absorption band, will decide that whether it will peak into the atmosphere, into the top layer it will peak, or it will peak to the lower level of the atmosphere. So lambda2 is basically, it is the medium sensitive. So that's why it is peaking somewhere into the mid of the atmosphere. So here the selection of wavelengths are very important for Nadir looking these sounders, because you can select the wavelengths, for example, any wavelength from lambda1 to lambda3, and you can decide that this particular channel will sense which layer of the atmosphere. So that's why by appropriately selecting the gases, it means which gas we have to select for the sounding. And the second thing, why we have to select the gas, because the sensitivity of the transmittance will vary only for the absorption thing. So that's why we have to select some gas which have some sort of absorption. We cannot select window channel for making a sounder kind of channel. The second thing is that we cannot randomly select any of the wavelength between the least absorption to the highest absorption. We must select wavelength in such a way that some of those channels will peak into the different layer of the atmosphere, so as to we can have sensitivity from the channels which are peaking into the different height of the atmosphere. So these channels must be contiguous, or maybe suppose if we want let's say suppose we have just two channel, lambda3 and lambda1, so we cannot have full profile. We'll have one information at the top of the atmosphere and another information just at the lower of the atmosphere. So that's why we must have some contiguous channels, so that the atmosphere is appropriately sensed at the different height. So that's why this channel selection is very much important. Now this is the mathematical description of the weighting function that shows that the atmospheric cross section, which is decreases with the altitude, and the transmittance, which is increases with the altitude. And if we multiply by with these two things, then we can have the weighting functions. So here, just to summarize, in the previous section, suppose if we want to know the temperature. So one thing is very important, like this term in the direct atmospheric term, which is the del tau by del P, is basically a weighting function, and B, it is the Planck function, which is dependent on the temperature. So if we just want to concentrate on these two terms, so there are two unknowns. We don't know the temperature, nor we don't know the transmittance. So suppose if somehow, if one of these quantities are a priori known, then we can compute the other things. Theoretically, we can compute the other thing. So for example, if we want to know the temperature, so we must know this quantity, this ratio del tau by del P, such that we know the a priori transmittances. So we have to choose some of that gas which does not vary very much high in space and time. So so for the temperature profile, we must choose some gases which has absorption in particular ranges, and that which does not vary very spatially and temporally. So these gases may be like oxygen and nitrogen, but nitrogen is basically lies, it is in the UV region, so it is not very useful for the IR and microwave sensing. So another gas is O2, which absorption lies in the microwave region. So that's why oxygen is chosen for the temperature sounding in the microwave. And we select CO2, though that it varies with the space and time, but its variation is not very high for the for all practical purposes. We can consider it as a constant, and we can provide that constant value, and we can retrieve the information of temperature. So that's why we require some form of uniformly distributed gas emitted radiance for the temperature profile. But once we know the temperature profile, then if we have the same kind of these channels basically lambda 1, lambda 2 in the water vapor absorption band. So once we know the temperature, then we can know the density of the gas. So that's why by appropriately selecting the various gases like CO2 and water vapor and combination of it, and if we have the appropriate channels, then we can simultaneously retrieve the temperature and water vapor profile. So here from this section, it is very much clear that how many channels we should have and what should be the bandwidth, because here I have shown just lambda 3, but for all practical purposes, it is not possible to generate a monochromatic kind of wavelengths. So there is always a wavelength interval and as well as the central frequency. So how many bands we can put and how much bandwidth. So how it is related with the its accuracy. So basically, I am just showing some of the spectral resolution. It means that the bandwidth of channels. So obviously, if there is a higher it is in kinds of a very coarser bandwidth. So obviously we can have very less number of channels, but as the bandwidth decreases to a smaller values, then we can have more number of channels. So these are some of the values of the various sensors like IIRS, CRIS, and current sounder like INSET 3D, and the imager like INSET 3D imager. So this is the some of the numbers for various instrument. So it is just an example that how this spectra, basically this is the BT of a typical BT spectra for the IIRS with the spectral resolution of 0.2 centimeter inverse. Now if just resample it to the IIRS or CRIS like spectra, then it is a 0.6 centimeter inverse. You see that many absorption lines are missing and it is losing some of the information content. Again, if it is like the further coarser resolution like 1.2 centimeter, we are losing much information like the less number of channels, and like the current sounder, our INSET 3D sounder kind of thing. So you see that maximum number of absorption lines are missing from this spectra. So it means we do have lower number of channels with the relatively larger bandwidth. So information content is relatively very small in comparison to IIRS and IIRS. And this is the imager for the INSET 3D imager. It is not used for the sounding purpose. So we see that as we, again, the same thing is put on the same figure, and we see that the same thing on the left plane panel, and we see its impact on its accuracy. So left panel shows that the accuracy of the water vapor and temperature. So it is very much clear that as we have more number of channels with the relatively lesser bandwidth, and obviously with the higher NEDT, because this is always a challenge as you go on for the more number of channels with the lesser bandwidth, then the NEDT is always a very a tricky parameter to handle. So, but here the NEDT responses of all these hyperspectral is as good as any multispectral channel. So we see that there is a considerable improvement from the coarser bandwidth multispectral sounder INSET 3D to IIRS, and we have the similar improvement seen in the temperature. So that's why nowadays people are more concentrating on the hyperspectral sounding from the IR kind of sensors. So this total sounding could be converted into the two parts. The first part is the forward problem, which says, suppose if you know the a priori information of the atmospheric state, then what will be the wavelength, or what will be the radiance at a particular wavelength is observed by the sensor. So this is the part of the radiative transfer equation. So here it is very important to see that this is the radiance at a particular wavelength, and this is the radiative transfer equation, which is basically solved numerically, and then we can compute the wavelength. But the thing is that it is the monochromatic spectral region. It is the spectral radiance. It means it is computed at a one particular wavelength. But as it has already been explained that there are multispectral sounder, it means there are not just one wavelength in a channel, but it covers a kind of a band of a wavelengths. So that's why we have to convolve it over the sensor response function. So sensor response function shows the behavior of sensor with respect to the different wavelengths. So basically in observation, we do not get I lambda, but we get R lambda. Basically, R is the total observation, which is integrated over a many wavelengths. So that's why computing all these radiative transfer equations for different wavelengths and then convolving it into the wavelength band, it is a very time consuming process, and we require a very specific radiative transfer model to solve these problems. So now comes to the retrieval part, and I'll cover it very quickly. So first part is very much I believe that it is understood that based upon our wavelength things, our wavelength thing, we can have this kind of information. Okay, it means the, let's say, temperature information or many gas information sampled at various height. So now what happens is we do have some sort of measurement, let's say some 100 or 150 or maybe 20 measurements, but we want to retrieve the temperature from 80 kilometers to the surface. So this basically continuous function is a temperature information. Okay, so what is physically appearing is there that the temperature is a continuous quantity, and temperature is a continuous quantity, but whatever we measure, whether in terms of 100, 500, 1000 or some tens number of channels, are basically discrete. So the problem is ill-posed. It is under constraint. Continuous function means we require infinite number of information from the some measurable quantities from some n number of measurements. So that's why first of all what we have to do, we have to discretize the solution. For example, instead of generating the continuous function, what we have to do, we have to basically discretize it. It means we will derive the temperature at any other gas at some particular altitude. So that's why by discretizing in terms of, let's say, taking the Fourier transform or many other methods are there through which we can discretize those particular atmospheric parameter depending upon the number of observations. The second thing is that, let's say, this information, whatever the number of channels here, as I have already shown here, that let's say there are 3 numbers, but as you increase the number of weighting functions, then they will start overlapping. It means even though there are 50 or 100 or maybe thousands number of channels, but obviously all this, even in this case, you see that the lambda 1, lambda 3 are overlapping at some point, and at certain points, even lambda 1, lambda 2, lambda 3 are also overlapping at some point. It means these weighting functions are overlapping, and the other thing is that no measurement is free from the errors. It means there is always some errors are involved in the measurement. So because of the overlapping of the weighting functions and the measurement in the radiances, like the inbuilt inherent errors, make it the ill conditioned. It means some of the sensitivity in the your measurement can result into the lot of inaccuracies in your estimation of the atmospheric parameters that you are going to derive from those measurements. So that I'm going to just show very quickly in this example. For example, this is the one equation. Let's say I do have just two measurement, x1 plus x2 is equal to 2, and another equation is 2x1 plus 2.01 x2 is equal to 4.01. So roughly, if you see that if I remove 0.01 from the second equation, 0.01 from the second equation, then what will happen? Basically, even though we have two information, but the two information is basically nothing but the duplication. We do have just one information here. It is the multiplication of the factor of 2. But you see that just the addition of 0.01 are making that as if these two equations are different. But what happens, like if instead of 4.01, if I make it simply 4. So this example shows that just by the measurement error or just because of the overlapping, even if we do have two channels, for example, two lines shown by the black lines, so it seems that they are intersecting, though they are almost parallel. Okay. So we can have unique solution, but what happens? Suppose if there we add some type of bias in the observation. If we remove like this bias, instead of like red and blue lines, suppose these two lines does not provide any solution, though they are same equation. But suppose if simply we make a kind of intercept, a very different intercept of the blue line, we can have a solution. So it means a bit of change in its bias can also produce a different result, which is basically is not intended by those observations. But the second thing is even more, you can say that more problematic. Instead of line, okay, suppose if this line, because of the measurement error, it is smeared into a kind of a rectangle shape. It means due to the measurement error, we cannot say that the observation is represented by a line, but a kind of a strip, very thin strip, kind of a very rectangle with a very thin breadth, and similarly two lines. So now you see that instead of intersecting at a point, basically there is a region of uncertainty. It means any solution which is shown by the gray area, just because of the measurement error, random error, we can have a n number of solutions because of this measurement error. So this degeneracy we have to remove. We have to make solution in a such a way that the solution should be stable. So here you simply say that it is a simply linear inversion, and through inversion practically you can see that there are n number of observations and n number of desired variable. You can make a linear equation, you can invert it, and you can get the solution. But due to these errors like biases and particularly from the random errors, these solutions are highly unstable because this A, this coefficient, if you invert it, can be a very ill-conditioned matrix, and that's why it will be very highly unstable solution. So what is the way out? So there are various ways to do that. So one is the very simple, but require a lot of effort. So primarily, though there is it could be a very problem which could be discussed at in a length. But here primarily we'll discuss simply touch upon three methods: statistical retrievals, physical retrievals, and hybrid retrieval. So in statistical retrieval, what we do, we simply kind of a robust regression kind of thing, where we can have a kind of a data set where we do have observations and corresponding matchup radio sonde observations, which covers almost all the variability of the atmosphere, and then we just generate a relationship between the observed radiances and atmospheric profiles. And with those coefficient, we can simply retrieve the atmospheric parameter as per our choice. So, but the thing is that these kind of equations require a lot of matchup data set, which is many times which is difficult to generate. and also sometimes it does not cover the Hoare variability. And the major thing is that these kind of solutions are not very dynamic, and it is not very much governed by the physics of the problem. So these are but the advantages, that it requires very computationally simple, does not require much computational time, and it does not cover the whole physics of the problem. The second thing is that the physical retrieval, basically here we have to first start with, it is a kind of a nonlinear optimization problem where we have to start with some sort of sensible guess, which is called as the first guess, that we consider that solution will lie somewhere near to this first guess. And on the runtime, the weighting functions are calculated. Then the forward problem is solved to yield the estimate of the radiance. And then the computed radiance are matched with the observed one, like the whatever we have observed. And if it is matching closely with this, the observed radiance, then we can say that the solution is converging. And if it is not matching, then we have to go back and appropriately, based upon the weighting function thing, that we have to appropriately change the some of the parameters, atmospheric parameters like temperature or moisture in the input. And then this process is basically repeated, iterated, and we see that if it is being basically converged or not. And if solution is converged, then we see that, okay, this is the final retrieved product. So this is a very useful, and in fact, one of the most used methodology across the missions, due to its you can say due to its proximity with the all physical steps, because here in runtime we compute the Jacobians or weighting functions in each computation. So that's why basically it is physically consistent with the observations, and that's why this is a kind of a physical retrieval for the given problem. But the major disadvantage with this thing is that it is very computationally intensive, and it rely on the quality of the observed radiances, because it assumes that the radiances are perfect and it is free from any kind of biases. The third thing is the hybrid retrieval. It is a kind of more is somewhere between the statistical retrieval and the physical retrieval. But they do not require a large training data set, because it starts with the some sort of training data set, but it does not compute the weighting functions online, and it computes the offline weighting function and try to adjust, like optimize the solution in a way like the physical retrieval, but not through the online mode. It is basically in offline, you compute the weighting functions and then try to, like it is sort of a constraint statistical retrieval. So this is the flow chart basically being used for the INSET 3D sounder retrieval algorithm, where this is the first guess, maybe comes from the regression or the atmospheric profiles, maybe generated by the hybrid first guess. Then you can compute the radiances, and then this radiances is basically go for the iterative mode. And then if it is converge, then we can say that finally we have some sort of physical retrieval. So before this thing, all these things are very much done, because IR observations are affected by the cloud. And so that's why the cloud detection or cloud clearing is done. And as I've already stated, it is based upon that there must not be any biases in the observations. So these physical retrieval basically relies on the radiance bias correction mechanism. So once all these things are done, then only we can go for the physical retrieval kind of scheme. So as I have already shown that the IR instrument is very much affected by the cloud, and cloud is nothing but the noise in the FOR for the sounders. So as we go higher in the spatial resolution, so we can say that the higher the spatial, like higher the coarser the spatial resolution, there is a more chance that there is a contamination by the cloud, and it will increase the noise in that pixel. So getting a very cloud free pixel in fact decreases as we go with the coarser resolution. But higher the spatial resolution, there is a higher chances of getting the clear pixels. So that's why for the IR thing, it is a very problematic for the cloud screening and then the cloud clearing. Even if there are some clouds, it could be cleared by some of the algorithms. So this is the methodology which shows that how these clouds are detected. So basically, cloud detection is a multi-spectral algorithm which uses several channels, like in the inset case 13.3, 12.6. There are these channels are listed here, and this is a series of tests are applied to check if that particular pixels is contaminated by the cloud or not. And to reduce the noise, once the clear pixel are basically averaged for the larger FORs, so as to the noise for those clear pixels are reduced, and then for the larger FORs, the basically it is that the profiles are retrieved. So this is the cloud clearing methodology. So it is generally done by using the those pixels where there are uniform clouds, and there is also the probability of having some clear scenes. So it could be done in two ways. By first is by seeing if the fraction of pixels which is not covered by the cloud having some ancillary information. For example, in Inset 3D, we can have this information of clear pixels by using the higher spatial resolution of visible pixels, so that we can have the exact cloud friction amount known in that particular FOR. Or we can have some information like microwave does not affected by the presence of cloud. So that fraction could be also computed by the combination of microwave observations over the footprint of various hyperspectral IR observation. And in fact, this is the very methodology is being used throughout the missions where the microwave and hyperspectral sounders are working together. So this is the formula through which we can compute the clear radiances by using the radiative transfer model, and then we can compute the cloud fraction. Once we know the information of cloud fraction, we can put it into this equation, and we can compute the cloud cleared radiance. So by using the cloud cleared radiance, the number of sounding increases, and we have the more number of soundings by the combination of microwave and IR or some ancillary information where we can have some fractional cloud information. So this is the cloud cleared information again, this thing. And so this is the way. I'll just go for the Indian geostationary meteorological satellite. It shows the total missions. And then this is the specification for Inset 3DS sounder. These are the various SRF put over the background BT of the IIRS, and it shows that the you see that the there are many spectral lines for each Inset 3D sounder SRFs. So it shows that it is the multispectral and have a lot of bandwidth in this multispectral sounder. So these, as I have already stated, that these are the 18 SRFs for the Inset 3D. This is the representative weighting function, and you see that the weighting functions are quite broad and they are overlapping. So that makes problem ill-constrained and ill-posed, and that's why the inversion of temperature and moisture profile requires a lot of computational effort. So this is the first glimpse of Inset 3D sounder, and here I can stop my presentation. So thank you.
Thank you, sir. We truly appreciate the knowledge you share with us. Now we have some questions. We will quickly take 1 and 2. There is a question by Narendra Gaur. How does ISRO plans to overcome 30% error in water vapor estimations?
Actually, this is a very, you can say, good question. That as such, we do not say that we plan for the 30% error. The thing is that it depends upon the what kind of instrument we are proposing. So it is a kind of a limitation with that instrument itself. So here, if we say that we are planning, like we have already launched 3 multispectral sounder in the geostationary orbit. And as I have already shown that the SRF, that the bandwidth of those channels are relatively large. So that makes weighting function little bit broader and overlapping. So this makes a problem in such a way that it is difficult to get accuracy better than 20-25%. But even though by using some sort of binning or taking the higher spatial resolution at the higher atmospheric layers, we can bit improve from 30% to 25% or so. But it is not a kind of a ISRO's thing for getting the 30%. Basically, it depends what kind of instrument you have chosen for the sounding. So it is the major thing from the instrument itself. So that's why actually it is a general term that the accuracy is around 30% for water vapor for the multispectral sounder.
Okay, sir. So that means there is another question by Sahib Pal. So is there a fundamental physics limitation of how accurate satellite atmospheric sounding can retrieve vertical temperature profiles?
In some way, the answer cannot be given straightforward yes or no. The physics wise, the thing is that the physics does not put the limitation on the retrieval accuracy. It is the thing that how great or how much the engineering limitation is put by the engineering team. Basically, if we can have a kind of a direct delta kind of weighting function, which is very difficult to achieve, because it is not possible to make instrument with the infinitesimally small bandwidth kind of channel. Even though kind of a FTIR instrument like IIRS, it is we do have 0.2 centimeter inverse kind of wavelength. So here the weighting functions are very narrow, and we do have a large number of channels like 8,400 number kind of channels, and that's why it makes a very accurate estimation of water vapor and temperature. But again, the sensor limitations like the NEDT, the bandwidth of the channels, the overlapping, etc. So it's a kind of a, you can say that the combination of physics and the engineering that makes we cannot say that we can have the very less 0.001% accuracy in water vapor and 0.0001 kind of accuracy in temperature, because of the both thing limitation with the atmospheric science, you can say, and the other thing is that the NEDT and the channel bandwidth. So it makes the problem complicated.
Thank you, sir. We will have one more last question. How can sounding data be integrated with ground-based radio sounding scales?
The thing is that radio sonde which are launched from the ground-based stations are considered to the truth for the atmospheric soundings, because they make the in situ observations, and it provides the observations at a very high vertical resolutions, and these observations are like, you can say that it is the test bed for any kind of space based and any other instrument that makes measurement. However, like the primary thing is that the highest impact on the atmospheric prediction, or maybe in the climate monitoring, the radio sondes are considered to be the best. They are considered to the reference. But wherever we want to have a large number of soundings, because radio sonde are point observation, we cannot have it on each and every place and at each time. So wherever we want to have some sort of atmospheric things which we require on the uniform grids are at the very higher temporal resolution. So what we do, generally we make a kind of a merge product which has the information from the radio sonde, from the various satellite systems, from the other ground-based observations like microwave radiometer, etc. So all these information are fused with the model outputs, and these reanalyzed and the analyzed products are generated, which are you cannot say it is as accurate as the radio sonde, but its accuracy are very closer to the truth. And the major advantage is that we do have a very high it is available on the each grid point at the very high temporal scale. So obviously many informations from the various sources are merged to generate a analyzed product.
Thank you, sir. Thank you for answering our questions. This ends our presentations. On behalf of everyone, I would like to express our sincere thanks for your informative and thought-provoking presentation. Now I hand over the session to Dr. Jagdish.
Yeah, we thank both the speakers for their time and the amount of preparation they have done. And we also thank both the moderators for conducting the session. So with this, we end today's session. Thank you. Thanks to all the students and coordinators for patiently listening to these talks. So with this, we